Before you tune another reranker, check whether Retrieval already lost the answer. Recall ceiling analysis makes that visible in Python. By the end, you'll be able to build a workflow like this, which compares relevance labels to candidates and reports whether Retrieval or re-ranking limits results. I'm Professor Pi, teaching search and IR with simple Python. Retrieval often decides the fate of your search system. A perfect re-ranker cannot fix what the retriever never returned. Recall ceiling analysis answers a simple question. How often does the retriever even include a relevant document in its candidate list? If that share is low, tuning the re-ranker is mostly wasted effort. Intuitively, recall ceiling analysis separates two sources of error. One is retrieval failure, where the candidates lack any relevant item. The other is ranking failure, where the candidate set contains relevance, but the re-ranker places it lower. Success looks like a high retrieval ceiling and a re-ranker that approaches that ceiling. On small data sets, this tells you whether to spend effort on better retrieval or on re-ranker features. We will build a tiny, repeatable workflow. It compares ground truth relevance labels to the retrieved candidate lists. Then it reports average recall, the top one theoretical ceiling, a simple re-ranker accuracy, and a breakdown of retrieval misses versus ranking misses. That way, you know exactly which stage to fix next. Now we'll compute average retrieval recall. This snippet computes average retrieval recall by comparing ground truth queries to candidate sets. The variable TURELs maps each query to its relevant document IDs, while CANS holds the retrieved candidates per query. For each query, the code intersects relevant IDs with candidates to count hits, then divides by the number of relevant documents to get per query recall. These per query values are averaged with mean to summarize retrieval coverage across the set. Here, K equals the length of each candidate list, implicitly setting the recall cutoff. If you expand candidates, recall generally increases until saturation. The printed average tells you how often retrieval includes something relevant at all. Next, we'll derive the top one theoretical ceiling. This example estimates the top one ceiling, the fraction of queries where a perfect re-ranker could place a relevant document at rank 1. The variable present counts queries that have at least one relevant ID inside the candidate set. Dividing by the total number of queries gives ceil 1, the theoretical maximum top one accuracy, achievable without changing retrieval. This isolates the retriever's gating effect on any downstream ranker. If your candidate depth or recall improves, this ceiling typically rises. If you shrink candidates, it falls accordingly. The printed ceiling shows the best possible top one result if re-ranking made 0 mistakes. Now, we'll try a toy re-ranker to see actual performance. This code applies a toy re-ranker that scores candidates by word overlap and measures top one accuracy. The mapping docs holds short texts for each document ID, and queries provides text for each query ID. The function OV returns the count of shared words between a query and a document, serving as a basic relevance score. For each query, Max selects the highest scoring candidate as best, and hits increments if that ID is relevant per queries. Finally, accuracy ACC is the fraction of queries whose top result is relevant. Increasing candidate size or improving overlap scoring should raise accuracy. The printed accuracy shows what your current re-ranker actually achieves. Next, we'll split errors into retrieval misses and ranking misses. This snippet attributes errors to retrieval or re-ranking, so you can focus fixes. For each query, the variable incand checks whether any relevant ID appears in the candidate list. If none appear, It increments ret miss, since no re-ranker could have succeeded. Otherwise, it selects best with the same overlap-based re-ranker and counts a ranking miss when best is not relevant per queries. This simple logic turns raw outcomes into actionable categories. If you increase candidate depth, retrieval miss usually drops. If you tune the ranker, ranking miss should fall. The printed counts show which stage is the real bottleneck right now. Now, we'll show how adding one relevant candidate changes the picture. This example raises candidate depth for one query to demonstrate how retrieval recall caps re-ranking quality. The new mapping cans2 appends a relevant ID to the third query's candidates, simulating a wider beam or hybrid retriever. It recomputes the ceiling as the share of queries with at least one relevant candidate, and then reuses the overlap re-ranker to measure new top 1 accuracy. Adding a relevant document converts a guaranteed failure into a potential success. Increasing depth further can improve recall, but may add latency. Balance K with system constraints. The printed ceiling and accuracy confirm that better retrieval lifts achievable and realized quality. In practice, this toy maps directly to real pipelines. Replace the overlap scorer with your neural re-ranker. Replace the candidate lists with results from BM25, semantic vectors, or an ANN index. The same measurements tell you whether to invest in better retrieval, a data augmentation strategy, or re-ranker architecture. Recap. What it is: a small analysis that measures retrieval recall and the top 1 ceiling. When to use it: whenever your re-ranker seems stuck and you want to know if retrieval is the bottleneck. One caveat: ceilings depend on candidate depth and relevance labeling quality. Next step: try increasing candidate depth for a subset of queries, or switch the retriever and measure how ceiling and accuracy move. That single experiment often tells you whether to tune retrieval parameters or to improve the re-ranker. If short, practical IR helps, subscribe and watch the IR videos.